Welcome back. Today we will do the remaining exercises inside standard library types. And as you can remember, we have done the exercises for iterators. And today we will do these four remaining exercises, which will be arc1, box1, cow1, and rc1. And we are inside standard library types, box 1. So let's dive into it. At compile time, Rust needs to know how much space a type takes up. This becomes problematic for recursive types, where a value can have as part of itself another value of the same type. To get around the issue, we can use a box, a smart pointer used to store data on the heap, which also allows us to wrap a recursive type. The recursive type we are implementing in this exercise is the const list, a data structure frequently found in functional programming languages. So, just a side note, const list actually originates from the Lisp programming language. Each item in a const list contains two elements, the value of the current item and the next item. The last item is a value called nil. So step 1, use a box in the enum definition to make the code compile. Step 2, create both empty and non-empty const lists by replacing to do. Note the tests should not be changed. Alright, so as you can see, we have here a public enum list, and this holds two members, cons, which holds i32 integer, and list. And then we have the second member, nil. So the problem over here is that this actually is recursive. So list, basically this enum holds itself as a type. So cons, we have i32 and then list, and we basically recurse over and over. So what we want to accomplish is actually to have a list which would look like that. We have 1 and then a new list, 2 and then a new list, 3, and in the end we have nil, like that. This is what our list should look like in the end. Now we have a problem over here. As you can see, recursive type list has infinite size. Recursive type has infinite size, recursive without indirection. So what is the problem? Well, basically all sizes have to be known at compile time. So when you compile a program, what Rust compiler will actually do, it will go inside a type, here an enum message, and then, because an enum only one variant will be used of it, Rust compiler will check which one is the largest. I guess in here it's change color because it holds 3 i32 integers, and then it will determine the size of the type message. And the problem we have in our program is we have recursion. So we have cons, and cons holds i32 and another cons. And then inside this cons we again have a i32 and another cons, and so on and so on. So Rust compiler cannot determine the size of list at compile time. That's our problem, because we are recursing over here. So the solution is to put list into a box. Now box is a smart pointer which means we are allocating a value onto the heap, store data on the heap. So there is basically two types of memory, stack and heap, and stack is a lot faster, but everything has to be fixed size. And on the heap we can allocate, and it's a little bit slower to then get the data out of heap, but we can reallocate without problem. So for example, an array is on the stack because it's fixed size, while a vector is on the heap because we can expand a vector. And what we want to accomplish over here is we will put the type list into a box, and then the size of list can be determined by the compiler at compile time, because box is just a pointer. So over here we just have the size of a pointer, and the pointer then just points to the value in the heap memory. So what we accomplished here is that a cons holds an i32 and a box which is of u size, because as I've said, we are just storing a pointer inside cons and not the value. Alright, and then in the main function we have two print line statements which basically just print out the return values of these two functions we have to implement. So over here, create empty list. So we just have to create an empty list which will look something like that. Nil. And nil basically just has always to be in the end of the list, as we saw before. So what we can do is just make list and nil, and that's it. As you can see, create empty list, this test passes. And over here, create non-empty list. So what I will create is a list like that, 2, 3 and nil. This is what our list will look like in the end. So we start again with list, and then we have a cons, and a cons holds two values, which is i32, and a box which holds list as a type. So we can go over here, I will put 1, and then over here we will make box new. So we create a new pointer, and then we can have another list cons which holds 2, and again a box new, and then we can have another cons which holds 3, and over here we put box, and we just put list nil like that. And this is basically what we saw before. We have 1, 2, 3 and nil like that. So let's see. As you can see, it's compiling. Now, to make this one a little bit cleaner, we can actually use an import. I will import list, and from list we want cons and nil like that. So we imported these two, so we can get rid of this one, like that. And over here I will rewrite it so we can use cons directly, and we have 1, and then over here we have a new box, and then inside here we have a cons with 2, and we create a new box, and then inside the new box we have 3, and again box new, which holds then nil, like that. So this is a little bit cleaner. We just used an import over here, or a use statement, and that's why we don't have to always type list cons, list nil. We can just directly put it like that, and this makes the code a little bit cleaner. And as you can see, we always have to use box because that's what's defined over here. A cons holds I32 and a smart pointer box which holds list, like that. So this box holds another list with cons member, and this holds another list, and so on. All right. The next one will be arc1. In this exercise, we are given a vector of u32 unsigned integer called numbers with values ranging from 0 to 99, 0, 1, 2 until 99. We would like to use this set of numbers within 8 different threads simultaneously. Each thread is going to get the sum of every 8 value with an offset. So the first thread, offset 0, will sum 0, 8, 16. The second thread, offset 1, will sum 1, 9, and 17. The third thread, offset 2, will sum 2, 10, 18, and the eighth thread, offset 7, will sum 7, 15, and 23. Because we are using threads, our values need to be thread safe. Therefore, we are using arc. We need to make a change in each of the 2 to-dos. Make this code compile by filling in a value for shared numbers where the first to-do command is, and create an initial binding for child numbers where the second to-do command is. Try not to create any copies of the numbers back, and yeah. As you can see, we have here use statements. We import arc and thread. So before we dive into it, I will just briefly explain why we use threads. So in today's computers, which are a lot more powerful, we have multiple processors inside. So maybe you have heard of dual core or quad core. So what this basically means is that the processor holds 4 cores for quad core, or dual core 2 cores. And that means that we can basically, if we have a program, we can create threads which then execute concurrently, which means each thread will execute independently from another thread, and also in parallel, which means that each thread will execute at the same time. And as you can see, we spawn a new thread like that, and this thread simply counts from 1 to 10 and prints out every number in each iteration. And in the main thread, so this is the main function, we count from 1 to 5 and print out every number on each iteration. And as you can see, we have also thread sleep. So in each iteration, the thread sleeps for 1 millisecond. And this allows basically, because then the thread will be blocked, and that means that another thread will execute. And that's why we then have, for example, number 1 from main, then number 1 from spawned, then number 2 from main, then number 2 from spawned, and so on. Now, as you can notice, we are in spawned thread, we are actually counting from 1 to 10, but only 5 of the spawned thread will actually get executed. And that's because if main finishes its execution, then automatically the thread also will stop. So it won't let the thread finish its execution. Now, there is also another concept. I want to go briefly over it, and it's join handles. And basically, a thread returns a type which is called join handle. And join handle is an owned value. And when we have a join handle, for example, here we have a variable handle, and it stores this join handle type, which is the return type of a spawned thread. And what we then can do is we can, on the join handle, we can call the method join, which returns a result type. So we have to unwrap it. And what join basically allows us to do is, or basically what join does is it blocks the thread currently running until the thread represented by the handle terminates. So as you can see over here, we call on the handle, that's this one, join. And what this does is, as you can see, then all the remaining numbers from the spawned thread actually executes, because main will be blocked if it finishes. This one, if it finishes, it will get blocked, and then handle can execute its remaining task like that. So, and of course, for example, if we place handle join over there, then firstly this thread will execute all of its commands and then the main thread. So it's also important where you place this join method. All right, let's see what we have here. We have numbers, which holds a vector of integer types, unsigned integer 32 from 0 to 100. Like basically in the example we have 0, 1, 2, and we have this until 99. Because as you can remember, this is a range, and if there is not an equal sign, then the last one is excluded, as it is over here. Then shared numbers. Now here we have our first to do, and what we basically want to do is we want to place the numbers vector inside an arc. Numbers like that. And as you can see, this then wraps this vector, which holds unsigned integers, into arc. Now what is arc? Here we have atomic reference counting with arc. So arc basically allows you to have multiple ownership, and it's basically the same as RC, which we will go into it later, but for multi-thread operations. So as you can see, if we place it inside arc, it then lets us clone the value, and then we can basically have multiple ownership, because each thread then takes this variable counter and modifies it. And this is important because we do not know which thread will hold this value over here the last. So arc basically counts the references of a value, and then if the counter is on 0, it drops the value. And we do that because we do not know which in which thread the value gets dropped, because as I've said, threads run in parallel, so we don't really know which thread will finish in the end, or which thread is the last thread which will finish. So that's why we need an atomic reference counting. So as you can see, we have put numbers inside this, and we have called it shared numbers, because we can then share this vector in all the threads we are spawning. So as you can see, here we have a join handle. So in here we have a vector which will hold join handles. And as you can remember, join handle is just a type that will get returned by thread spawn. So over here we have a for loop for offset in 0 to 8. So in the first iteration, offset will be 0. And then let child numbers. So over here, we then can use arc clone. And then we pass it shared numbers, like that. And this has to be a reference. So you might now ask, why didn't we clone it directly? Like that, for example, shared numbers dot clone. Why didn't we do it like that? And the reason is because arc clone won't actually clone it directly, so it won't create a deep copy of this variable. It will just create a pointer which also points to the same location as this shared numbers variable is in heap memory. And that's basically all we do. And then we have here join handles push. So we push the result over here in this vector. And what will get pushed? It is a thread. As you can see, we spawn a new thread. And here we have move. So move basically means it captures the variables in the environment and takes ownership of it. So over here you can see we have child numbers. This is outside of the thread, so it will take ownership of this child numbers, and then we create an iterator and we filter. Now filter takes in the what's it called, in the closure, it takes a reference. So we have to dereference it, and then we put modulus 8 and we check if it is equal to offset. So for example, in the first iteration, we have offset is 0, and then we basically have child numbers, which we will be iterating over it. That's this vector with these values 0, 1, 2 until 99. And then we filter. If, for example, 0 modulus 8 is equal to the offset, which is 0 in the first iteration. And if it is, then, as you know, filter will create a new iterator, so it will then store the values of this operation, and in the end it sums up all the values in the new iterator that filter will create. So as you can see over here, offset 0 will sum 0, 8, 16 and so on. So let me just check that everything I said is right. So we have offset 0, and then we take child numbers, which is this shared numbers. Shared numbers holds the numbers over here. Then we check if, yeah, for example, we have 8 modulus 8 will be 0. And basically we have an offset, so offset 0 will sum 0, 8, 16. For example, if we take 16 and put it over here, we have 16 modulus 8 will be 0. 16 modulus 8, and I always do it like that. 16 divided by 8 is 2, so nothing remains, and that's what we have over here. We wanted to have offset 0, so this will get then this will return true, and then in the end it just sums up all the values in the vector that return 0, because in the first iteration we have 0, and that returns 0 when we put modulus 8 on it. So for example, 8 modulus 8 will also be 0, because 8 divided by 8 is 1, so we don't have a remainder, so it will return 0, like that. That's what we see over here. Now, for example, in the second iteration we have offset 1, and then the modulus operation should return 1. If this then returns true for a number in the vector, then, as I've said, filter will create another iterator with only the values that have that returned true over here, and we in the end consume the iterator and call the sum method on it. So what that basically means, for example, if we have offset 0, we have 0, 8, 16 and so on, and it just performs addition operation over all these integers in the numbers that have returned true over here. I hope that's clear. And then all we do is we print out the sum. We print out the offset, which is for the first iteration 0, and then the sum. And this we will do in each iteration, and as you can remember, each iteration does this in a separate thread. So all of these will run simultaneously. And over here, as you can see, we have our join handles. This is a vector of join handles. We put it into an iter. It has then ownership. And then for each handle, we call the join method and unwrap. And this is because the join method will return a type of result. And as I've said, join just make sure that every thread over here will execute until it finishes. So let's see, is this compiling? And as you can see, it is compiling. All we did here is we created arc over here. We put the vector of integers inside this. And as I've said, arc allows us then to have multiple ownership. So we then can clone this vector we have over here. And what this allows us is that each thread can basically access it and has ownership, because clone over here just creates a new pointer to the location of shared numbers. And that's basically it. Now, as you can see in the output, it starts with offset 4 and then 1 and then 5 and then 0. And you might ask why? Because we have a for loop, and the for loop starts with 0, then 1, 2, 3 until 8. And that's exactly what I try to explain, because we have threads in here. And threads run concurrently, and that means that each thread runs at the same time. So this can lead to that the order will get messed up, because, for example, here this thread offset 4 just finished executing faster than this one, and this is the last one. And that's exactly why we need arc, because we don't know which thread will drop the value. We have here numbers, this vec. We don't know which one will drop it the last. So we need arc, which is basically a counter. So each time we clone this value, the count will get incremented. And each time a value gets dropped, the count will get decremented. And if the count is at 0, then the memory will get deallocated, because, as you remember, we store this on the heap. A vector is stored on the heap, and that's why we need to do that. All right. Let's see the next one, and this is RC. It's that one. And I don't really know why they start with arc and not with RC, because RC is basically the same as arc, but it's just for, so basically arc is for multi-threading and RC is just single threading. So I think they just should have started with RC, because it's a little bit simpler. But anyway, in this exercise we want to express the concept of multiple owners via the RC type. This is a model of our solar system. There is a sun type and multiple planets. The planets take ownership of the sun, indicating that they revolve around the sun. Make this code compile by using the proper RC primitives to express that the sun has multiple owners. So as you can see, we are importing RC. So what is RC? Using RC to share data. So RC stands for reference counting, reference counted smart pointer. So RC is also a smart pointer, and it basically allows us to share ownership. So as you can see over here, for example, we have B, we have Z, and we have A, and all of them point to the same data in the heap memory. So as I've said, smart pointers always are connected to the heap memory. And now, as you can see, this is important. We use the RC type when we want to allocate some data on the heap from multiple parts of our program to read, and we can't determine at compile time which part will finish using the data last. If we knew which part would finish last, we could just make that part the data's owner, and the normal ownership rules enforce that compile time would take effect. Note that RC is only for use in single-threaded scenarios. And yeah, so using RC to share data. We share ownership when we use RC. And RC basically is really the same as arc we used in the previous exercise. So that's basically the program which tries to imitate this over here. And as you can see, we have here, that's what we implemented actually, and we want to have box new which then holds this value, and in C we have box new which also holds A. Now this is not possible because A will get moved to here, and then we can't move it again. Value moved here, value used here after move. So this then gets moved into B, so we can't then use A again because this variable has been moved. So what we can do actually is just we make this RC, and that means that this type over here can have multiple ownership. So then, as you can see, we have to wrap it around here, and then we can clone, and that's basically like in arc. Cloning here means that we just create a new pointer which points to the location in memory of A. Like that. Okay, and reference counting, it basically means that every time we clone like that, the count will increase, and every time a value gets dropped, the count will decrease, and if it's on 0, then it will get dropped. And we use that, as I've said, because we don't know at compile time which variable will hold the type that gets dropped in the last execution. So over here, as you can see, we have a struct sun, and we have enum planet, We have here various planets, and all of them holds referent counter to Sun. That means that we can then share this struct with multiple different members of this enum. And as you can see, we implemented for planet a method details which just prints hi from and then self, which in this case just refers to the name. So we have the sun, we create RC new and sun, and then we have one reference to sun because we have created one here, RC new, which will hold one reference to sun. Then over here we have planet Mercury, which holds RC, as you can see, Mercury RC of type sun. And then we can actually clone RC and we pass it a reference to this sun variable, like that. And then we have two references of this sun. And as you can see, then we print out the strong count. Strong count means just how many references are there which cloned this RC type. And as you can see, always if we clone sun, we increase in reference. So each planet gets assigned a copy of sun, which is not a deep copy again, but we have ownership over this value. And then, as you can see, we have to implement it over here too. And as you can see over here, we drop the various planets. And always when we drop one planet, the reference gets decreased. And when we reach 0, then the value sun will get dropped or will get deallocated from memory. So in the end, we just have one reference, which is sun. All right, and let me actually over here, because I have to see the two, I'll do it like that, like this. Okay, this should be fine. So as you can see, we are implementing these and we have to do, it's like that. So what we actually have to do over here is we have to clone sun. Like that. And over here it's the same thing. We clone sun, and over here again we clone, like that. And all we have to do over here is just dropping the values. Now the values get dropped in decreasing order. So after Mars we have after Mars we have, what do we see over here, Mars, and then we have Earth. So we drop earth. Then over here we drop Venus, that's this one, and then Mercury. Like that. And this should then compile. As you can see, the code is compiling, and as you can see here we see the reference counts, and after dropping, the reference count gets decreased on every drop, like that. Now I think what we could also do over here is just RC clone, and then inside here we can RC new, and we have sun, like that. And this is not possible. Alright, this is actually not the case. Alright, now we have to clone a reference to the value we want to clone. We clone this because this holds RC new sun, like that. Alright, this is compiling, as you can see, and let me close that one. Right. Now the last one will be cow. This exercise explores the cow, or clone on write type. Cow is a clone on write smart pointer. It can enclose and provide immutable access to borrowed data and clone the data lazily when mutation or ownership is required. The type is designed to work with general borrowed data via the borrow trait. So cow actually is something, honestly, I've never used, but I can see that it can be useful in very specific situations. So cow basically is an enum, and cow stands for clone on write smart pointer. So the type cow is a smart pointer providing clone on write functionality. It can enclose and provide immutable access to borrowed data and clone the data lazily when mutation or ownership is required. The type is designed to work with general borrowed data via the borrow trait. So as you can see, you can pass something to cow, and then it checks if it is borrowed or if it's owned. And then when you need the passed value to be mutated, it will then make it mutable, or basically it clones the value you have passed over here, but that's only in case if it is needed. For example, if you mutate something. So if it's not needed, it won't do anything. As you can see, we have here absolute all, and we have 2 lifetimes because actually cow requires a lifetime. As you can see, you have to pass it a lifetime and a slice. Now this argument will hold a reference and with this lifetime, because as you remember, we have to specify lifetimes if we have a reference in argument and we return a reference. So we basically make sure that these 2 over here have the same lifetimes. and we return cow with a slice of I32 integer values. So as you can see, we start in main, we have a slice over here. This is basically an array. And then we pass to cow from a slice of this array. And a slice basically means we take an array like slice, that's this variable over here, and we take the first element until the last element. So this would be the same as I've written like this, 0 to 3, like that, because 0 to 3 we have here 0, 1, 2, and 3 will be excluded, and we pass a reference of that. And this is basically a fixed type, and this is the same as when you have from a string to a string slice, like that. Basically what this does is it takes a string. You have, for example, string from hello, and you store that in a variable, let's say hello. Let's do it like that, and then what we basically will do is we will take hello and do it like that, like this, and this then will be a string slice. And of course this is fixed size, you can't modify it after that, and that's basically the difference. And of course this is owned and this is not owned, like that. So we pass cow a string slice, and then we call this function with the string slice, or basically with the cow type. As you can see, we have here input is of type cow, which holds I32 slice. And you don't have to put here ampersand, because this will actually get added automatically. So B will be to owned, like that. All right. And then, as you can see, we are matching the return value of this function. And if the return value is cow borrowed, as you can see, that's this one. If it's borrowed, then we print I borrowed this slice, and else we panic, because we expect this to be borrowed. As you can read here, no clone occurs because input doesn't need to be mutated. So what this function actually does is it goes through the array and takes the values, and then if one value is smaller than 0, if it's negative, then it will make it positive. And that's what we call absolute, because absolute, if you're coming from C, you know, the ABS function, it makes just absolute means you have, for example, -5, and it will make it 5, like that. It's pretty simple. And as you can see over here, we have an array, but it doesn't even have a negative number. And that's why we pass the slice to cow, and then this will get this type of cow will get passed over here, and then cow checks. So we have here passed to cow a string slice which doesn't hold any negative numbers. So a clone over here is not needed because we don't modify anything over here. So what then cow returns is just borrowed. And that's what's get printed over here. Now in the second example, clone occurs because input needs to be mutated. And as you can see, this time we have here an array which holds in fact a negative number. So this element over here has to be mutated. We want it in the end to be like that. Let me make it a little bigger. We want it in the end to be like this, because as I've said, we want the absolute numbers, which in this case absolute is 1. So again, we make a cow from a slice of this array, and then we pass it to abs all. And this is a mutable reference, of course, because this argument over here actually has to be mutable in case we have to modify a value inside it. And then we match the return type, and this type cow will return, or this function will return cow owned, like that. That's this one. I modified this slice and now own it. So basically here cow clones into a vector, and then we can make it to mute and modify the element inside the vector or inside this slice we have passed. This is actually not a vector. Right. So this is owned then because we have modified it, and cow made it owned like that. And now no clone occurs because input is already owned. So over here we have a vec. As you can see, it's not an array like this or this, it's a vector. And this vector holds -1, 0, 1, and we create a cow from this. And of course, vectors are owned. Vectors are owned types. So we pass it over here, and then we call it the absAll function, and we pass it input, which, as you can notice, this is an owned type. Of course, we pass it a reference because that's what's expected over here, but inside cow, this will be already owned. So clones into a vector if not already owned. So this is already owned, so there won't be a clone. Cow won't clone anything because it's not necessary. It can just immediately mutate the element inside the vector. And that's why when we match the return value from this function, which returns a value of cow or of type cow, then we actually get owned over here because this is already owned. So I own this slice, should be the return type, and we get back a type of cow owned. That's this one over here from the cow enum. Let's see. And as you can see, it's compiling. The output is I borrowed this slice, I modified this slice, and now own it, and I know I own this slice. So I honestly never used it that much, but as you can see, it's pretty useful if you have something which you're not sure or not sure, but you can basically put it like that. It's very useful if you have some types which are owned and some which aren't owned and you don't know that. So basically cow will then determine if it needs to be cloned or not. All right, and that's it. The next topic will be threads. So see you then. Goodbye.